Okay, here we go. First video of linear algebra for our online portion of this course here. This is going to be great. Alright, so a couple things before we jump into it. First off, the audio at the beginning might be a little janky. I don't have a fancy microphone, so for some reason I haven't been able to fix that just yet. So there'll be like this weird hissing, and then it figures out the volume of my voice. I don't know. But anyway, we'll have fun. And today is really fun, actually. This is fun material. So we're going to finish up talking about Chapter 4 today. Specifically, we'll get the last odds and ends about bases for vector spaces, specifically sections 4.5 and 4.6. So something else that you should be doing is pausing this video a lot, right? Because we're going to be doing proofs, and you've got this benefit of you can kind of pause like every time I put up a step and kind of read through it and really think of it. And have pen and paper next to you while you do this. But, yeah. Alright. I think that's all the preparatory things I wanted to mention, but let's get into it. So let's start off by reminding ourselves what we've been talking about. So we're talking about bases for vector spaces, specifically a type of basis that's called a Hamal basis, as we discussed in person. And these are subsets of vector spaces that do two things. First off, they span the vector space, meaning that the span of the set B is all of V, and that the set is linearly independent. Okay, so to be a basis, you need to check two things. If you're proving something is a basis, you have two things to do. Show that it spans, and show that it's linearly independent. Now, that means you do two things. So, first off, the spanning part means that for any vector out of V, we can find a linear combination of elements out of B that equal V. So in other words, I can find scalars, alpha 1 to alpha n, and vectors x1 to xn. Note the vectors coming out of B, so that V is a linear combination. You can scale those up and add it, and you get V. The second thing we need to check is the linear independence, and that is done by picking distinct elements out of B and scalars, so that when we scale them up and get the zero vector, the only way that goes down is if all of the scalars are zero. So in other words, the only way to create the zero vector in V, the identity element, is with trivial scalings. Right, so the only linear combo is the trivial one. So you just multiply by a bunch of zeros and add them up. And again, it's worth stressing the distinctness part here, as I've been doing, because a lot of the theorems that we want for linear independence require these things to be different from each other. Note that in the span, we actually do not care. There's no requirement that they're distinct here. So, worth stressing. We saw in class a couple of spots where you really need to be stressing that these are chosen to be different from each other, and that will rear its head coming up. But alright, so that's what a basis is. Jog our memory. Let's get some nice examples. So, like I've said, always think of R2 when you're doing linear algebra. R2 and R3 usually never steer you wrong in terms of how things are going to look and behave. And the go-to basis for R2 is 1, 0, 0, 1. Very nice. Something else, I forgot to mention in the beginning, there is a problem list that's due. Probably a good idea to have that open, or the problems written down as we're going through this, because as per usual, I am in no way going to give you hints or tell you what to do, you know? Absolutely not. Right, so maybe one of the problems is demonstrating that something is a basis for R2, like negative 1, 1, 1, 1, I don't know. Beats me. I didn't write those problems. Alright, well, for R2, we can go from there. R3, you could do the same thing where you've got three vectors, 1 in the appropriate spot, 0's elsewhere, and nothing's stopping us from doing this for R, 4, 5, 6, 7, 12 billion grams number, whichever your favorite gigantic positive integer is, and you make a basis by having that number of vectors with zeros everywhere except for 1 in the key spot. So here you can imagine a vector E sub k, has 1 in the k spot and 0 everywhere else. This is usually referred to as the standard basis for Rn. And if it's called the standard one, obviously it means there are others. We'll talk about those. Alright, now for a more exciting example of a basis, now note the distinction here. The set of polynomials, if we look at 1, the function x squared, the function x cubed, so on and so forth, that set is linearly independent. Right, pick any finite subset of it, scale them up, and if that's equal to the 0 function, a polynomial is a 0 function only if the coefficients are 0, so it's clearly linearly independent, and every polynomial is just a linear combo of those things, so it's a basis. Now note that this basis is infinite. These bases we saw up here are finite. Ooh, exciting. Whoa, it's gonna get crazy today. And so recall the last thing we proved in class, I think, if I remember right, is that in fact you can demonstrate that every vector space has a basis. The key ingredient for this proof is that any linearly independent subset either spans your set, so it is a basis, and if it fails to be a basis, that means you can actually extend the linearly independent subset. You can make it bigger. Pick anything that's not in its span and add it to the set remains linearly independent. So, by exhaustion, you always have to have a basis, because the empty set is linearly independent. So, you could start from there and just keep throwing stuff into your set until eventually you get a basis. Now, we know that proof was a little hand-wavy, but it's legit. You can make it, there's a way of making it a lot more precise, like I was saying, with these more advanced set theoretic tools like the axiom of choice. Specifically, Zorn's lemma is the thing that you use that's equivalent to it. But it is worth noting, for those of you that care enough about this, logically, you actually can get away with a weaker assumption, something called the Boolean prime ideal theorem, because sure, why not? Anyway, alright, and as we mentioned, every vector space having a basis has kind of some weird consequences, especially when you've got infinite dimensional bases. Infinite dimensional bases, those are the types of vector space you study in a branch of math called functional analysis. And as I promised, the last week of the course will be a grab bag of topics I find fun and interesting. Infinite dimensional linear algebra is my jam, so maybe I'll talk a little bit about that. And one of the most famous unsolved problems above infinite dimensional linear algebra. It's going to be good, let me tell you. Anyway, alright, so we know vector space has a basis, but now as we just saw, we have bases of varying sizes. So R2 has a basis that has 2 elements in it. Rn has a basis that has n elements in it. Well, that's convenient. And the set of polynomials has a infinite set as a basis. Now note, we do want to stress this is an infinite set, but it is a countable infinite set. There is a list. And oh boy, 201's coming back. And it wants revenge. Alright. So that's the main goal for today, and actually for pretty much the rest of this exciting presentation. We are going to demonstrate that any 2 bases for any given vector space has to have the same size. So any 2 bases that you can create have to have the same number of things. So R2, any basis for R2 can only ever have 2 things. R3, any basis can only ever have 3 things in it. The polynomials, any other basis, can only have countably infinitely many, that's what I meant to say, elements in it. Right, so there's no basis for the polynomials with only finitely many things. Now, when we talk about size, and you're dealing with finite and infinite, that means you need to deal with cardinality. So in other words, 2 sets are the same size if there's a 1-to-1 correspondence between them. Okay, so let your mind drift back to 201, meaning that if 2 sets have the same cardinality, that means I can create a bijection between them, a function that is injective, 1-to-1, and surjective, onto. We're adults, so we don't use 1-to-1 and onto, but if you like those words. Alright, so that's going to be the main goal. In fact, that's going to be the big crescendo for what we're going to do here. Right, and like I just said, that means that for, like, R2, there are there's only one possibility for the basis. It has two elements. So that allows us to meaningfully define the dimension of a vector space to be the size of its basis, right? Because any bases are going to have the same amount of stuff in them. So calling R3 a three-dimensional vector space is completely legitimate. And the polynomials can then be called an infinite-dimensional vector space, because any basis that you can formulate is not finite. And in fact, if you really wanted to be careful, you would say countably infinite-dimensional. That does mean there are uncountably infinite-dimensional vector spaces. So, for example, the collection of all continuous functions is one such crazy example. But we'll get into that. Maybe we'll get into that. We'll see how far off the deep end I go in the final video for the course. All right, so that's our goal. That's what we're going to do, and as you can see, a number of slides. We still have like 11 to go. So, well, that means we're going to have a good time. Now, what's even more fun and a good time about all of this is that this is pretty new of a result. I double-checked this. I looked up when this was actually proven, and it was proven in 1934, which that's kind of fun, right? Because math has been around since the dawn of time, so anything that's not even 100 years old yet, that's always fun, right? And that shouldn't be too surprising, because as I mentioned, vector spaces themselves weren't fully formulated until the early 1900s, specifically 1911, 1913, somewhere around there, by our good friend Giuseppe Peano from the homeland. So we're doing this whole online thing because of, oh, by the way, here you go. You can't stop me from going off on a tangent. So if you want to, like, skip to this time code or something. I'm not editing these videos, you kidding me? One and done. But anyway, I was talking to my grandmother, who is first generation from Italy. She is aged. She's in her late 80s. And she was talking to me, and she's like, I haven't heard from my cousins in Italy. I'm pretty sure they're dead. And she's like, they're in their 90s, so that was a fun convo with Grandma while we're in the middle of a pandemic. All right, so fun fact. So this is a relatively new result, and the not so fun fact, as I already pointed out, this is going to take a while. This is a big theorem, very important. I can't even begin to stress how essential it is, especially because it allows us to talk about this idea of dimension, right? That's something that in math, oh boy, what did I just do? Oh no, I'm keeping that in, you can't stop me. All right, yeah, I was trying to highlight, but I double-clicked. Yeah. Rookie mistake. Anyway, it allows us to define dimension. Now, dimension is sort of this intuitive idea, right? Like, precisely define what dimension means. And, this is one possible explanation, but it does require you to have a vector space to talk about dimension. Now, that works really well for R2 and R3, but there are objects you can draw, and you kind of go like, well, this really isn't one or two-dimensional, what is it? Those sorts of things are called fractals, and that stuff gets off the deep end. Speaking of which, fall 2021, if we make it, I'll be teaching a course on dynamical systems, Math 495, special topics, and half that class will be about dealing with fractals, and one of the things you do there is try to come up with, like, what do you mean by something having dimension 3/2? So note, this dimension needs to be a positive integer, or it's potentially an infinite object. But anyway, that's enough rambling for me. So let's go ahead and prove this fact. It is going to take a couple of slides and a couple of ancillary results to get there. And while we go, we'll pick up some fun things along the way. Okay, so the first thing we're going to prove to get a handle on this is the following. If you have a distinct number of vectors in Rn, and you've got more vectors than n, so for example, if we're in R4 and we have 12,000 vectors, then that set needs to be linearly independent. Okay. Now, if you think of a smaller example, let's say I'm in R2, if I have 3 distinct vectors, they need to be linearly dependent. Alright, this shouldn't be too surprising. This seems pretty legit. Now, how do you prove this, right? Because I can claim this, and intuitively we can go like, well, that makes sense, because my intuition, again, is built off of what I already know about how Rn feels. I already have this idea of what its dimension is, right? And that's what we're trying to prove today, is actually grab that mathematical feeling and make it nice and precise. The poetry of logical ideas. Alright, so this proof is actually really straightforward because it's a good old contradiction. Suppose it was. Alright, well, if 1 to m was linearly independent, that means the subset 1 to n needs to be linearly independent, right? Any subset of a linearly independent set remains linearly independent, so you can't have a dependent subset inside of an independent one. Now, I have, hey, n vectors in Rn, I can make a matrix. Specifically, I can make an n by n, the kind of matrices I like, whose columns are the vectors x1, x2, x3, all the way to xn. Alright, now what do we know about those vectors? We know that they are linearly independent, and they are distinct. Again, the distinctness is important here. Well, as we proved, that means the matrix has to be invertible, which means that the matrix equation always has a solution. So I can always find a vector, C, in Rn, so that A times C, the matrix A, equals the vector x sub n plus 1. Okay, right? So, unraveling the definitions here, I'm assuming independent. I've got an independent collection of vectors. They are distinct. I know that when I make that matrix has to be invertible. And what do we know about invertible matrices? We know that we can always solve the matrix equation. And before we even do it, you might notice it. Your brain notices it if you're not picking up on it. We're already done with the proof. Now, why are we going to be done? Because this matrix equation, remember, can be turned into a vector equation. Specifically, if I let C be the vector in Rn whose entries are C1, C2, so on and so forth, this matrix equation is the same thing as this vector equation right here. And what does that vector equation say? Well, x sub n plus 1 is a linear combination of the vectors x1 to xn, but that would mean this set was linearly dependent because there is an element that is a linear combo of the elements inside the set. But we assumed we were independent, so we got a nice, exciting contradiction. So there we go. Beautiful. All right. Now, this is a great proof. Let's sit here and digest it for a second. While I keep myself hydrated. I've noticed in these videos if I don't drink liquid while I'm going through it, throat gets dry and scratchy. It sounds bad. It already doesn't sound great, but, you know. Doing my best. Forgetting the rest. Okay. Now, there needs to be a period right there. Oh, God, unwatchable. Alright. Anyway, now that we have this, before we keep going, do a little sidebar here. Like I was saying, in R2, if you've got 3 vectors, like this, we know, without having to do anything, that we are linearly dependent. There is no hope for these to be independent. We just proved that you can't do it. So that means I can find scalars A, B, and C, so that that vector equation holds, and at least one of the scalars is non-zero. And in fact, it's pretty easy to verify that the scalars that would work are -1, 2, and -1. And it is worth noting that there are actually a lot more choices. There's infinitely many. Now, another way of interpreting this result, if we think about these vectors 1, 4, 2, 5, 3, 6, very creative. If you cram these together, that becomes a 2 by 3 matrix. And another way of thinking about all of this is you've got, 3 unknowns, but only 2 equations. So, Yeah, probably can find infinitely many solutions, so probably can't guarantee that all the scalars are zero. So that mathematical intuition, that mathematical feeling, there we go. We've now got a super precise, exact explanation for why that happens, right? If you've got too many variables and not enough equations, that is exactly what this theorem is telling you is going to happen. There's no way to get that nice, unique solution. All right, beautiful. All right, well, let's look at another beautiful result. So the result we just proved was for Rn, right? So our usual exciting Euclidean space. In fact, that exact result can be proven for any single vector space, right? And here it is written in precise vector space language. So given a vector space, n vectors, and m vectors in the span of those n vectors. So in this case, if this was Rn, the vectors x1 to xn would be the usual standard basis vectors. And this x1 to xm, which is distinct and has more things in it than we have in xn, then this set's going to be linearly independent. So this is basically what we just proved, but instead of Rn, it's good for any vector space. Okay. And in fact, we are going to use that result to prove this. Okay, but this one we're actually going to be able to do directly because, well, we already proved the previous result, and basically what we're going to do is encode that previous result in terms of vector spaces. So this is really going to be the first time we see using Rn to prove stuff for general vector spaces. Okay, so what's the method of attack here? Well, again, unravel the definitions. What have we assumed? We've assumed that the vectors y1 all the way to ym are in the span of that set. That means I can find scalars, so that they're linear combos of things out of x1 all the way to xn. So I can find a collection of scalars. Oh, hey, look, they have two indices. It's like I can make a matrix or something. All right. So yeah, there you go. Now, the thing to note here is that we can now, like I just said, communicate this information in a different way. We can create vectors C1 all the way to Cm, whose entries are chosen accordingly. I didn't mention it before, but with Rn, like I said, it doesn't matter if you write these vectors horizontally or vertically. I'm going to stick with horizontal for these slides because the vertical ones take up too much space, and I don't want the slides to be like, I don't want 1,000 slides. So anyway, all right, so you got your exciting vector C there. Now, we're dealing with independence, so we want to make sure we got distinctness here. Those vectors I created have to be distinct because my vectors y are distinct. Note that if like ci was equal to cj, then this formula right here would tell me that y I is equal to yj, which would not be true because I've assumed they are distinct. Right, so I would force I and j to be equal to each other if they weren't. All right, cool. So here we want to stress we've got the distinctness. That's coming from the distinctness of y. Note that I actually didn't need x1 to xn to be distinct. That's actually kind of interesting that you don't need that. And in fact, it's never used anywhere in the proof. So that's fun. But anyway. Okay, so what have we just done? We've taken the assumptions, which are about vector spaces, and I took that information and I converted it over to information in Rn. Specifically, I took my m vectors and associated vectors in Rn to each one of them. They're distinct, and oh hey, they're in Rn and I have m of them, and m is bigger than n. So, moving to the next slide, I know that they're linearly dependent, so I can find scalars, so that when I scale and add them all up, I'll get the zero vector in Rn, and at least one of the scalars is non-zero. I don't know which one it is. One of them is. I don't care. I know that at least one of them isn't. So what am I going to do now? Well, I'm going to basically convert this equation into the vector equation, right? Because my elements v, if we pop back over here, my elements y are coming out of vector space v. And basically what I'm doing is representing them in terms of Rn. So what I want is to show that if I replace C1 with Y1, Y2 replacing C2, and all the way up to Cm being replaced with Ym, then instead of the zero vector in Rn, I have the zero vector from the vector space, so Z sub V. Now, how are we going to pull that off? Well, note that these are vectors in Rn. So if I were to look at each entry individually, specifically pick any entry j between 1 and n, so again, these are elements of Rn, so they have n entries. If you look at each one, you'll see that this equation needs solved, and there needs to be a plus there. Oh yeah, watch this move. This is what I'm going to do here. Where's that plus? I'm missing a plus. It's right there. Okay, alright, yeah. You can't stop me. Changes detected. Oh, wow, I'm really glad it's actually still working. And there you go, there's the plus sign. Should have fixed that period from before. Well, we'll see. I'm going to go look at the video, and if it crashes, I'm going to be very mad because I'll have to do this video over again. Anyway. Okay. But yeah, so we've got that plus. It's exciting. And that's not... Oh, that's not right either. Oh, boy. Oh, boy, oh, boy, oh, boy. You see, look, I even have it, like, ready to have the freaking M in there. You know what happened there? I'm going to tell you a little secret. That I'm a hack fraud, first off. Second off, I didn't have it as M, I had it as N+1 originally. And then a little bit later on, we're going to see I actually need it to be a generic M. I can't have it be N+1. So that's what went wrong there. Not my fault. Anyway, fixed it. Okay, yeah, let's keep going here. So, yeah, so you pick any entry J, right? These are elements out of Rn, so look at any one of these entries. We know that this formula needs to hold. And how are we going to use that formula? Well, if you let your mind pop back over to here, I'm going to hit all of these y sub i's with alpha I, and I'll get alpha I ci1, alpha I cin, and note that, oh, hey, look at that, I got those right there. Yep. So, I'll scale up all of those y terms I just talked about, and then notice, alpha 1, c11, then right below it would be alpha 2, c12, all the way down to alpha m, cm1. That means when I add all of these up, the x sub 1 term is going to get killed because the coefficients are going to be this summation, and that summation we know is 0. That's good for j equals 1, j equals 2, j equals 3, all the way up to j equals n. So all of these terms on the right, when we add all of this up, will all go to 0, and thus we've got my vectors y1 to ym. I can scale and add them up, and all of the scalars are not necessarily equal to 0. One of them is non-zero, so we have directly proven that that set is linearly dependent. Nice! That is a cool proof. That is a real slick one. This is actually the hardest proof for today. That goes without saying. But this is a really slick proof, really cool. And again, like I said, a really important one for us because this is the first time that we've really taken Rn and embedded the information we got out of it into the vector space. So it's really the first time we've seen that, and this is a really, right, kind of like a nice little watershed moment. And in fact, this is a very, 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 very common technique when you're studying vector spaces because it's an abstract general object, and while that's good, when it comes time to prove things, you use, more concrete objects as your intuition. And the fact that we're able to directly use it in the proof, that's very nice. And like I said, that's something that you do a lot with vector spaces, is basically, well, it worked in Rn, let me crowbar it into my vector space. And I'm not joking when it comes to that. It's something you do all the time. So, beautiful. All right. So, that's kind of cool. All right, now, time for another sidebar. Time for another indulgence, if you'll allow. And you can't stop me. I'm going to, because I'm just recording this in my guest room. And we have no time limit, so take that, I guess. I'm not, sorry, I don't mean to be antagonistic. I love you. All right. So, there's something that we can do here now that we have that proven, we can prove something very important. A theorem that's going to make it really easy to create bases for vector spaces. Specifically, let's say we're in the situation where we've got a vector space and it has been spanned by a finite number of elements, x1 to xn. Again, note here, I don't need to know beforehand that these are linearly independent. Or distinct even, I just know that I have n of them and they span the set. Then, for any distinct linearly independent collection of vectors, that needs to be a basis, right? So if you have n distinct linearly independent vectors, that must be a basis. Note, y1 all the way to yn, not necessarily even related to x1 to xn. You're just in the situation where you are being spanned by a finite number of elements of the set. Then any distinct linearly independent collection is going to be a basis. Okay, now how are we going to prove this? Alright, well note that we only need to do one thing, verify that the set is actually spanned by the elements y1 to yn, because they're already linearly independent to begin with. So, suppose not. Well, we can find something then that's not in its span, and hopefully you know where this is going, because I already planted the seed in your mind. That means, if I make my list a little bit longer, if I include y in my list, note that y is not in the set, y1 to yn, it's not in the span, so it can't possibly be in the set. Not only do we know we have a larger, distinct set, we also know that it has to be linearly independent, because as we discussed way back on slide number 3, if you have a linearly independent set and something that's not in its span, you can extend your linearly dependent set, because a linearly independent set, any linearly independent set either is a basis or it can be made larger. And oh, hey, looky here. We have 1, 2, all the way up to n plus 1, a number that's strictly bigger than n. We have distinct, they're linearly independent, but I can't have that because they are in the span of n number of things. That is in direct contradiction, oops, went the wrong way, to this theorem right here. If you've got a collection of m vectors in the span of n things, where m is bigger than n, they need to be dependent. So, if we had a collection of vectors that did not span the set, well, that can't possibly happen because we'd be able to extend the set, make the list bigger, and then, boom, contradiction. So, if I want to verify that we have a basis for a vector space that has been spanned by finitely many things, you just need to find that number of things distinct and linearly independent. So, in other words, in Rn, bases can be constructed by finding just n linearly independent vectors. You don't have to do anything else. So remember, when I said that proving something was a basis, you needed to prove that it spanned the set and was linearly independent. Well, it turns out that for Rn, no you don't. You just need to know they're linearly independent. They have to span them. So for example, 1, 2, 3, 4, 5, 6, 7, 10. The determinant of that is -3. That is a collection of distinct vectors. Well, I know that the columns then for the matrix formed by those are linearly independent, so I have 3 distinct linearly independent vectors in R3. It's got to be a basis for R3, as we just proved. So actually showing that a set is a basis in Rn, all you need to do is verify it's linearly independent. It must then be a basis. So this is incredibly powerful because it basically means that you don't need to do half of the proof, so we like that. But it also tells me that that set spans R3. And it may not be clear beforehand that that would even be true, right? Because that means that every vector in R3 is a linear combo of these vectors. Nice. That's kind of neat. Now, that's something you can verify if we think about it again, because this matrix has to be invertible, which means the matrix equation always is a solution. So the fact that every vector can be a linear combo, maybe that's not too surprising then, that would be true. But quite nice. So when it comes to Rn, verifying that something is a basis, You just need to verify it's linearly independent. If you have enough linearly independent vectors, it is a basis. That's nice. That is incredibly nice. That is great news. And it's worth noting that this is truly something that's only good for Rn. This does not work for the polynomials, for example, because if you were to look at the collection of polynomials of the form 1, x squared, x to the 4th, x to the 6th, so on and so forth, that's a linearly independent subset, but it doesn't span the set. Right, even though it has the same number of vectors as the normal basis does, right, because they're both countably infinite. Yeah, so unfortunately, this move is truly an Rn-only move, so, but it's good. So, for example, on problem 1 on your problem list, technically you don't need to do half of it, you just need to prove it's linearly independent, which, oh boy, if you just set up a matrix that says determinant, oh, real easy. Speaking of your problem list, problem number 3, we can actually push this even further. Because, let's say I have a subset that's linearly independent, but we don't have enough stuff. So this you could verify is a linearly independent subset of R3. Right, not too hard to see because I can't scale the first vector to create the second one, right, because I have a 0 here, so I can't make 1. And likewise, I have 0s here, so I can't make 1s over there, so there's no way of scaling them to the others. So this is linearly independent. If I wanted a basis, I just need to attach one more vector, and I just need to make sure that the vector I add will keep it linearly independent. Okay. Now, there are a couple of ways of doing this, actually. So your textbook has a completely different method than the one I'm going to show you. Your textbook's method is to basically go, well, I know what a basis for R3 is. It's the standard basis, the 1, 0, 0, 0, 1, 0, 0, 0, 1. And then they go, well, if you throw that in there, then you've got a linearly dependent set, and so there has to be scalars to make everything equal 0, and then from there you set up a matrix and you do some row reduced echelon stuff, and that tells you which unit basis, which element out of the standard basis to add to the set to make it a basis for the whole thing. You can check it out. I'm not a particular fan of it. I like the following. So, note that if we were to attach a vector, call it A, B, and C, the only way for that to keep us nice and linearly independent would be if that determinant was non-zero. And, ooh, hey, look at that. The determinant doesn't require anything about B, so B can be whatever you want. The only thing you need is to make sure that C is not equal to A. So as long as A and C are different, this will always create an exciting basis. So I like this method a little bit better because it tells you exactly what things are going to work. And note that there are infinitely many things that will work. That shouldn't be too surprising. Now, this method is massively unwieldy if you're in, like, R17 or something like that, because, as we discussed, determinants beyond 3x3s are just, yeah, they're fun. But anyway, so for us now, if I want to extend the set up here and create a basis, well, I just got to pick A, B, and C, and as long as I don't pick C equal to A, I've got a basis. And the one I went with is 1 square root of pi 0. Totally a basis. Right? I don't know if you'd ever want to use this, but there you go. This is a basis for R3. Square root of pi came to the party. It was a good time. Yeah, kind of neat. Alright, so I like that method. Now note, if there weren't enough zeros to make the determinant nice, maybe it's not the best method, but I like it better than the way the book does it, where the book's like just keep adding vectors until we know it's dependent, then row reduce, and whatever. It works. Check it out if you're interested, but I like this method. And if you want to do it for the third problem, I'd be appreciative. Or you can do it the way the book wants you to. That's fine too. I don't care. I like this one again because the book's method is to just add a standard basis vector, and you just got to make sure you pick the right one that doesn't cause any repetition to occur. But yeah. I don't know, I like this one so you can create goofy-looking bases. So. And goofy-looking bases, I mean, this might look dumb, but you're surprised sometimes some good, oddball thing works. Square root of pi, though, I mean, yeah, that's dumb. Let's get that out of here. Let's keep going on. Okay, so we still haven't done the thing that we're supposed to do, which is prove that every vector space, given the two bases, they have the same size. We're almost there, because now we got to prove the key ingredient, the last technical result today. Now, in the literature, this usually gets a name. I've seen it called the dimension theorem or equivalent sorts of things. This ends up being the key thing, and in particular in the proof that every two vector spaces have the same basis, this is the key step you need to do, and particularly our good friend Lübig, this was the main thing that he figured out and proved. Alright, so we're going to go and prove this, and note that it looks very similar to what we've basically proven. So we proved this result for Rn, then we proved it for vector spaces V, basically saying that if you have a number of vectors spanning a set, and you've got a linearly independent set, the number of things that are linearly independent cannot exceed the number of things out of the set E. So note the other way we were phrasing this, if we bop back here, is that if we had too many things in this set, that's in this span, then they have to be dependent. So we're going the other way with this particular result here. We're going with, well, if you have a linear independent set, there can't be any more of those than you have in E. Right, so before where we had n things in my set E, and we proved that n plus 1 or more things would be dependent. This is proving it the other way. Alright, so this is the full-blown generic version of the past couple of results we did. So we did this result for Rn, then we showed how it embeds into a vector space V, and now we're going to push it further and show that, in fact, that theorem is going to hold in a much more general type of way. Right. Okay, so we're going to prove that the cardinality of S is less than or equal to cardinality of V. In other symbols, we usually write cardinality like this. We use absolute values for the size of the set. I've also seen the pound sign for cardinality, for card, a number of things. I don't know. Yeah. So we're going to prove that S has as many things in E, E potentially has more. Okay. Now, when I say prove, I want to really stress that the proof I'm about to do, much like our proof that every vector space has a basis, is going to have a moment where we kind of just go, yeah, this makes sense, right? And then we just move on. And so there is again, a very powerful set theoretic tool that we're not explicitly using properly, but for the purposes of this class, we don't need to go too nuts. Alright, so here's how the proof works. We want to show that X has just as many things as E. And so note that if X is in S, that means X is in V, which means it's in the span of E, which means I can find finitely many things out of E so that X lives in the span. Okay. And in fact, you can find a efficient set. There is a smallest set that does this. It's not hard to prove such a set exists, but we don't need to do it. Basically, you know there's an n that works, so it's a non-empty set of integers, so you know there's a smallest, and then you can prove that any two sets of that size have to be the same. So there is a more appropriate way here. We just need to know that you can find finitely many. So for each element x out of S, there are finitely many things out of E that X will live in its span, right? That's just what it means to be in the span. You can find finitely many things that are a linear combo of it. So what does that mean? That means that if I take a distinct number of things out of S, it has to live in the span of the union of all of these sets EX. So note what I did here. For each X out of S, I associated a subset of things out of E. X1 is in the span of EX1, X2 is in the span of EX2, so on and so forth. So if I union all those up and span them, then those vectors X1, X, I need to live in that span. Okay. So what does that get me? I don't know why there was a pause there, but there was. Now, we've got linearly independent, we have n of them, and they are in the span of this set right here. That means this set right here has to have n things in it. If it had less than n, then the fact that these things were in there would force this set to be linearly dependent. But that's contradictory. Right, so these things live in the span of this collection, and as we just proved, if this collection exceeds the number of things we have on the left, that means if the number of things here in this set is not as much as the stuff we have here on the left, that stuff needs to be dependent. But we've assumed it's independent. So these elements, x1 to xn out of S, they live in the span of this union, and that union has to have at least as many things in it. Cannot have less, because then it would be dependent, which we've already proven is a contradiction. Alright, and like I said, this is mildly hand-wavy, so here's the hand-wavy part. So that means that for any number of elements in S, I can always find just as many elements in E. If you give me 100 things in S, I can find at least 100 things in E. In fact, I could probably find more, right? Because I have this union, which has at least n things in it, as we proved, at least 100 for the example, right? So for any number of things in S, I can always find just as many in E. So in other words, the cardinality of S is less than E. And you cannot see me, but I am flailing my arms around all over the place because I would really need to make this a lot more precise, even though intuitively everything I just said seems like it works. And indeed it does. And this proof is completely legitimate if we had access to a little bit more set theoretic tools. Specifically, the thing I'm using right here is called Hall's marriage lemma, which I think maybe in combinatorics they cover, but I'm sure the one guy who was in combinatorics who I forget in class who was like, yeah, we don't do that in combinatorics. When I was writing out that summation, I was like, oh, this is a notation they use. And I said no, and I'm like, well, yeah, probably. I don't know anything about combinatorics, so I'm infinite dimensional, man. That's like not. It's like the antithesis of combinatorics. But anyway, so it turns out that there's a more precise rule we can use here to help us. But this makes sense, right? For any number of things in S I can always find just as many in E. So E has at least as many things as S. All right, cool. Now, equipped with that, we can finally prove the big theorem for today, the star of the show. If I have a vector space V and I have two bases, then they have the same cardinality, which we write like this. All right, now how does this go? Well, the dimension theorem, the thing I just proved, you just use it twice because, well, B is a basis, so it spans V, and H is a basis, so it's linearly independent. So by what we just proved, H cannot have any more than what B has. B has at least as much as H. And then just swap the symbols. H is a basis, so it has to span. B is a basis, so it's linearly independent. B cannot have any more than H. H has at least as much as B. So they have to have the same things. Right, now note, when we talk about cardinality, the real precise thing is when you write, so for example, H cardinality less than B, that means that you can demonstrate that there is an injective function from H to B. There is a one-to-one function. Likewise here. Now note, the proof I didn't really create the function. I just said, well, clearly I could make one, so. Which, not the most valid mathematics, but good enough. And note here, as you discussed in 201, or hopefully you remember from 201, if you have an injection from H to B and an injection from B to H, you can actually create a bijection. This is the Cantor-Bernstein-Benedictson theorem. Sometimes it's just called the Cantor-Bernstein theorem, but, you know. Anyway, and that's actually a non-trivial theorem. That one's a little tricky to prove. But anyway, boom, here we go. We have now proven that given a vector space, if you've got two bases, they have to have the same cardinality. So dimension is well defined. It's the size of any basis you pick for the set. Any basis for your vector space always has to have the same number of things. So R4, any basis for R4 will only ever have 4 things in it. So we can clearly say that R4 is 4-dimensional. It is spanned by a linearly independent set with 4 elements. All right, and so we say that R is 4-dimensional, and we'll write dim of R4 is 4. things of that nature. Yes, and like I said, the idea here is to try to capture the intuitive idea of dimension in precise mathematical language. So for R4, that works out pretty well. Now, there is one set that we need to talk about that does kind of have a little bit of a weird behavior. Recall that in any vector space, the span of the empty set is the zero vector. The empty set there spans that set, and the empty set's linearly independent. So that means the empty set is a basis for the vector space that consists of only the identity element. That means it's got a dimension, right? Because every vector space has a basis, and as we just pointed out, there's a way of defining dimension. This is actually what we call a zero-dimensional vector space. And in fact, there is only one zero-dimensional vector space, the vector space that just has the identity element inside of it. Right, so we refer to this as zero dimension, and we write that the dimension is equal to zero. So dimension is actually a non-negative integer for finite dimensional. When it's infinite dimensional, it's technically a cardinal, and that's going off the deep end. You don't need to go that crazy. But that's worth pointing out, that we can talk about zero-dimensional spaces. And note, it's not that it's the set that has nothing, which the name would seem to indicate. It's the dimension of the singleton set that just consists of the zero vector. All right, remember, that set is a true blue vector space. It's super boring because there's exactly one thing in it, but it satisfies all of the axioms. So, worth noting that this exists because every so often the extreme cases do come up, and we do want to keep them in mind. All right. Okay, well, we're on the last slide here, so let's set up what we're going to do next. And let's set it up with a question. Is there any difference between R3 and a three-dimensional vector space? R3 is three-dimensional. And so for an example, if I look at the polynomials of degree less than or equal to 2, they have 1x, x squared as a basis. Any polynomial with degree less than or equal to 2 is a linear combo of those vectors. Those vectors are linearly independent, as we know, because the bigger set that contains all of those is independent, so this one needs to be linearly independent. So is there any real difference between R3 and the collection of polynomials that are real less than 2? Well, the answer is, well, they're completely different, right? R3 is a collection of ordered triples. 1x, x squared, the linear combo of all those are polynomials. Those are completely different objects. Now, that's true. They are not equal in the usual sense of equal. But in the eyes of dimension, they're both three-dimensional. And as we are going to learn, they really are the same vector space. Even though they look completely different, they're representing the exact same vector space. They're just a different representation. Ooh, well, we're going to need to make that precise, because that's a big statement. That's a big idea. Ooh. And there we go. First video done, and it was coming in at a whopping 53 minutes. Oh boy, oh boy, oh boy. I apologize. But I don't. Like, comment, and subscribe. See you next time.